So today we're going to look at some other notations for vectors and also describe, instead of breaking the vector down into a horizontal and vertical component, we're going to look at describing its position by using the angle to say which direction it's pointing in. So first we'll define another notation. This is based on something called a unit vector. A unit vector is a vector that has exactly a length of 1. And you can make unit vectors going in other diagonal directions as well, but the most common use of a unit vector is to describe the vector that has a piece going straight to the right a length of 1 or straight up a length of 1. And those two unit vectors, the length going straight to the right is defined as I, and the vector going straight up is defined as j. So sometimes you will see vectors written, instead of by using the angled vector brackets, they will instead use the scalar multiple of the vector I, because if you multiply this first vector here by 2, then you would have 2 comma 0, so it would have the horizontal piece of 2. And then if you did 3 times the vector j, you would have 0 comma 3, which is doing the vertical rise of 3. And by adding those two vectors together, the horizontal and vertical pieces are combined separately, you get the vector 2, 3. So using this I and j operation notation is another common way of describing a vector. So do make sure you understand how to write vectors using this. Essentially, you can just take the number in front of I, that's the number in the x component, and the number in front of j is your y component, since you're just multiplying them by 1. Another thing we're going to discuss is the direction angle. So there are two ways that we will use the direction angle in this class. One of them is when you know the magnitude of the vector and you are given the direction angle of the vector, then you can find the component form with those two pieces of information. The vector v will equal the magnitude, so find its length using the formula we discussed earlier, and multiply that by cosine of the angle they gave you. If you multiply those two pieces together, the magnitude and cosine of the angle, that'll give you the horizontal component of the vector, and then you can do the same thing multiplying the magnitude times sine of the angle to get the vertical component. So the two entries you get for this will be your horizontal and vertical pieces, and that will define your vector v. So this is useful when you don't actually know what the horizontal and vertical components are, but you know what angle the vector is pointing at, and you know how long the line is supposed to be. Another thing you can do with direction angles is find the reference angle when you know the component form. So maybe you already know the horizontal and vertical pieces, the x and the y values, and you're trying to figure out what angle that vector is pointing at. Well, you can find theta by doing tangent inverse of the y piece divided by the x piece. Now, what you have to be careful about on this is remembering that the inverse trig functions, they only give you one of the two possible answers. So when you're doing inverse tangent, it's going to give you an answer in the first or the fourth quadrant. So if you get an answer in the other quadrants, you have to remember how to add or subtract 180 to get the equivalent reference triangle angles out of that. So don't just hit tangent inverse of y over x and then stop there. Think about which quadrant your vector is in. If it's going to the left and up, if it has a negative x value and a positive y value, then what you will actually need to do is add 180 to the answer you get from the fourth quadrant, because putting it into your calculator will give you a fourth quadrant answer like negative 45 degrees, but you need an answer in the second quadrant, so you'll just add 180 to get it into the right position. If your vector has a negative x value and a negative y value, so that it's in the third quadrant, then again, you should be adding 180 to your answer because your calculator is going to spit out an answer in the first quadrant. So you need to flip it and get the answer that's going into the third quadrant, so it has the same reference triangle, because essentially it gives you the answer going up and right, but we need the answer going down and left if you have both a negative x and a negative y value. And then the last case is for when you get an answer in the fourth quadrant. Your calculator will spit out something as negative 45 degrees, but we want the coterminal angle for that. We want to know how far you're rotating counterclockwise around, so you're going to find the coterminal angle by adding 360 degrees to that. So just be aware of this, that if you are finding the direction angle, make sure you think about which quadrant your answer's in. First quadrant, you don't have to do anything special to. Second and third quadrant, you need to add 180 to your answer. And fourth quadrant, you need to add 360 so that you get the coterminal angle that describes how far you go around counterclockwise. And then that will describe the angle as far as which direction the vector is pointing at. So first, let's look at an example where they give you the direction angle and they give you the magnitude. That's what this is indicating here. So the previous formula that I gave you guys was to break this down into the horizontal and vertical pieces by doing magnitude, and in this case they're showing that the length is 18, times cosine of the angle, and make sure your calculator is in degree mode for this since this is a degree angle, and then use that same magnitude number and multiply it by sine of the angle. Now, this particular question doesn't tell us exactly what to round to, but always check your directions because the different MATLAB assignments and textbook assignments will have you round to different values. For now, I'm just going to round to 3 decimal places. That's usually kind of a good standard for these. So I'm going to put 16.314, and then for the vertical piece, 7.607. So now we know how far the vector is going to the right. It has a base of 16 and it has a height of 7.6 approximately. Now we're going to find the magnitude and direction angle of the vector 3i minus 4j, and this was that other notation we started off the notes by talking about. So remember, that just means that we have the vector positive 3 and negative 4. So if you prefer that notation, that's fine. You can just start off by rewriting it that way. Just make sure you understand what the sides of the triangle that we're making out of the vector are based on this information. Okay, so finding the magnitude is not new. This is something we've done before. So the magnitude of the vector v, our notation for magnitude, is the absolute value of v. And it's essentially the distance formula. Now the distance horizontally is given to us as 3. And the distance vertically is given to us as negative 4. So we're just going to be squaring those numbers, adding them up, and then taking the square root. So in this case, 3 squared is 9. Negative 4 times negative 4 is 16. And these would add up to 25, and the square root of 25 is equal to 5. You might have already expected this answer because you saw that this was going to make a 3, 4, 5 triangle. Now, the next part, the direction angle, this is what's new for us. So to find our direction angle, we need to take tangent inverse of the y value divided by the x value. So negative 4 over 3. And then the problem with this is the fraction negative 4 over 3 is the same as the fraction 4 over negative 3. So it could have been going left and up instead of right and down, and your calculator is not going to be able to distinguish between those two cases. So that's why we will have to consider which quadrant is our vector actually in. And in this case, if you're going right 3 and down 4, you should see that this is a 4th quadrant vector. So when we get our answer, that's where we're going to refer back to the information I gave you here. We're going to have to add 360 to what our calculator gives us, because it's going to give us an answer that does not describe the counterclockwise rotation around. We want to know how far we're going around the angle going counterclockwise rather than just the clockwise piece, which is what our calculator would tell us. So go ahead and hit tangent inverse of negative 4 divided by 3. And the answer I'm getting is approximately negative 53.130. But we don't want that clockwise angle, so I'm going to add 360 degrees to that, which makes the direction angle we're interested in positive 306 degrees, 0.870. So this would be the answer we actually use for our angle measurement. And then our magnitude was found up here. So just be careful about looking at where your vector is, seeing which quadrant it's in, and then adding the appropriate number to make sure that your answer is describing what we want, the counterclockwise rotation starting from due east. The last thing we're going to look at is another way to perform vector operations. We did vector operations in the last section of notes where we talked about how you can add two vectors together or how you can multiply the vectors by a scalar number. So another way that you can perform vector operations is by drawing the vectors and lining them up from head to tail. Now, the order that you pick the vectors in does not matter. If you have two vectors u plus v, you can draw u and then draw v starting from where u ends, Or you can do it the other way around. I'm saying you can draw the vector v first, and then wherever that one ends, you can draw u next. So the order that you pick the two vectors will not matter. Just keep lining them up from head to tail. And then once you finish all the different paths, all the different pieces, you're going to draw a vector going from the very beginning position to the very ending position. And that line will be your vector operation. That will show your final answer. So here's an example. We have a vector u and we have a vector v, and we're going to find the component form of 2u plus j. So I'm going to draw these vectors separately. I'm going to do the u part in red. Now, vector u is saying to go right 1 and up 2. Because remember that this is in component form 1, 2. And vector v, I'm going to do this one in blue, is saying to go left 3 and down 1. So it doesn't matter if I do the red or the blue vectors first or second, the order doesn't matter, but I'm going to choose to do the red one first. So I need to go right 1 and up 2. So that means I have a small vector starting from the origin and ending there. But it's not just u, it's 2u. So I can either double that length or I can just do a second u. Either way, mathematically it's the same idea. You're doubling the length of u or you're doing u twice. And then from where that one ends, now I'm going to switch to the other vector because now it's saying add the vector j, which wants me to go left 3 and down 1. So from my ending point, I'm going to go left 3 and down 1. So now I have a vector that ends there. But my final answer is based on going from the very starting position, the origin in this case, and ending at the final position over here. So my final answer is this black line. This one is my actual final answer, and this is the one that's showing the vector operations graphically, the 2u plus j value. Now, like I said, if you want to try to redraw this on your own, it's good to see that I could have done the left 3 and down 1 vector first, and then from there gone right 1 up 2, right 1 up 2 again. You can see that I would end up in this exact same spot, and then again I would still draw from the starting position to the ending position. So no matter what order you do these in, your final vector is the one that combines all of those together. It's the final ending position. So that's all for the notes. Like this.